you would ask me in grad school if I ever saw myself on my own free will writing up a lecture about stratigraphy and presenting it to, you guys aren't all freshmen, but essentially, freshman science class students, I would have laughed in your face because my stratigraphy teacher was an ass in all of this. He should have been an engineer. Not that engineers are, but they're a unique kind of. If you've met an engineer, they're very specific and so on and so forth. And he was one of those. And geologists usually aren't. All right. There is engineering geology. There is, certainly room for that sort of folks in geology. But stratigraphy, you wouldn't think would attract them. So you probably wondered what is stratigraphy, right? What is strata? What does strata mean? You've seen that word around in a handful of cases.
Layers. Like that.
Okay, and in math, what does it mean in math?
It means like stratified, like that. Divided into each group or something.
Oh, okay. I'm not familiar with it in math. That's what I was wondering. You said
Layers.
Layers. Okay. You got clouds that use that word. We use it with sediments for strata. And there's a handful of other. It's a fairly useful prefix, so to speak. Oh, that doesn't sound good. So, yeah, you're looking at strata right now. See the layers in that rock? That's strata. Sometimes they call it beds, bedding planes. But it's the study of rock layers. I'm like, oh, right? That sounds horrible. Why would I want to study rock layers? Well, folks that had lab yesterday actually kind of got a foreshadowing on this one. Because the rocks can tell us stories if we look at it right. Each layer is sort of a page in a book. And we see this most with sedimentary rocks. Because it's just sediment piles up on top of sediment, piles up on top of sediment. Think about it as dust in your house. All right? I'm sure you're all avid dusters, just like me. So, we wouldn't, what we've seen, we've been to people's houses that don't dust. And we know that, just a layer of fine stuff builds up. And over time, you could actually write your name in that stuff if it gets thick enough. All right? Just like that, at the surface of the earth, sediment builds up. You know from the sedimentary rock chapter that at some point it gets squeezed down and glued together, and we call it a rock. And stratigraphy deals with that aspect of it as well. But it's what's in between those layers, what's trapped in each layer, be it a fossil or some sort of marking, pattern, whatever you want to call it. You'll hear all about it. That can tell us something about these rocks, because we've only been around to take records for so long. Okay, dinosaurs may have wanted to keep records, but they didn't have thumbs, so they couldn't write. What we got, for the majority of the Earth's history, are rocks to look at. Sometimes it's simple. You see lava. Oh, there's a volcano here. How do you know that? Well, lava comes out of volcanoes. And sometimes it's not so simple. And everywhere in between. I kind of hinted the other day, well, I didn't hint, I told you, but I didn't make a big deal about it, that anywhere you see limestone, there had to be salt water, what we would essentially call an ocean. Yeah, there's a few inland sources of salt water, but generally speaking, okay, bless you, limestone only comes from a marine environment. So does that mean when you're driving down Route 90 and you see limestone that there was an ocean there? Yes, it does. All right, that falls under stratigraphy. So there's all kinds of things, not just that horrid stuff that he beat into our heads, worrying about grain size and this, that, and the other thing. Now, mind you, it was grad school. You're supposed to, amp things up a bit, so on and so forth. But anyway. So, yeah, stratigraphy's cool. I never would have thought I'd say that. Now, I'm a paleo guy, paleontology, so I study fossils, and it is essentially right down my alley. But it also just goes to show you sometimes how a teacher can just ruin something for people too. So just because you get a bad teacher doesn't mean the subject isn't good. Keep that in mind as you go through. You guys got a handful of years left of college, hopefully. Keep that in mind. Don't let their grumpiness dissuade you. So you've been looking at some rocks here. You've been looking at it. It looks like sand, right? One could assume, probably then, that this is what kind of rock we're looking at. Yeah, sandstone, maybe. It's not the best picture, but we're in a desert. There's a good chance it's been a desert for a while. Sand does pile up in layers, right? So, yeah, probably sandstone. The cool part about this is that picture you've been staring at for the last 10 minutes is on Mars. Okay? So we'll forgive them the picture quality. It's pretty damn impressive, actually, that being considered. But everything we just talked about, how sand works and everything else, and water and so on and so forth, if that's how you get sedimentary rocks to form, then those processes had to have occurred on Mars as well, at least at some point. It looks pretty barren right now. There's some ice here and there. But to see a lot of the stuff that we see, there was not just standing water, but flowing water. You got a question? It looks like you're pondering something.
They found water on Mars, right?
Ice. Okay. Yeah, it's really cold there. They don't have a whole hell of a lot of an atmosphere. They're smaller than us. Possibly plate tectonics has stopped. And a handful of other things. They don't have the kind of atmosphere we have anymore. And that's the other thing to look into it. Okay, we go all the way back to the solar nebula theory. I think we talked about that they're all the same age, and essentially the same age. And we can look to the left and see Venus, look to the right and see Mars, and compare and contrast with us. So even though they don't have water now, apparently at some point they did have an atmosphere. Apparently at some point they did have water. Because it's not just these layered rocks, we see stream beds and deposits, just like we see here. And yes, there could be other ways of making them, but that's the easiest and simplest way, and you kind of have to consider that first. I think it's Occam's razor. I don't know if you have had philosophy yet, but you really need to rule out the simplest things first before you go on to the extreme. So yeah, and it's red. So that tells us there was iron there, and that iron was able to oxidize. That needs oxygen. It's the red planet, for crying out loud. So, so all these things tell us stuff. And it's not just applicable to here on Earth. So there's that same outcrop. I think the other one was a zoom in. But I just got back from Arizona. I've been in Utah. This doesn't look too much like California, but you go into any of those deserty states in the middle there, it looks exactly like that. And it's the one and only kind of nod I'll give to those whack jobs that think we faked the moon landing. But a lot of the terrain, looks scarily similar. So sediments are deposited in layers. All right, I've said that a couple times already. Hopefully it's kind of obvious. We call those layers beds, sometimes bedding planes. I often just call them layers. So bedding is visible layering within the rock. Those of you that had lab yesterday, we were looking at shale and mudstone, and I told you the big difference between shale and mudstone was the appearance of visible layers. All right. right? This is a great example of another use of that word. Also, because of gravity and a handful of other things, but mainly gravity, those layers tend to be flat, horizontal. I'm just going to zoom back here to this picture for a minute. All right. They're all flat, like a stack of paper, a stack of cards, whatever. Even in water. All right, you would think like a picture of a lake. You don't get a bowl-shaped deposit because of gravity. That pebble rolls all the way down, or that piece of sand rolls all the way down, and it fills up the lake from the bottom up. You don't get a depression-shaped deposit. Now, we see slanted beds. We see beds that look like a roller coaster. That tells us, again, something else, that something happened. And then you get to go in and figure that out. It's kind of like CSI, but with rocks. Sounded cool for a minute and then not cool again. But yeah, let's get back to Earth. Up at the top, you can see it a lot easier. Down at the bottom, you've got all that riffraff that's fallen off the cliff over the years. Obscures it. But even that, sometimes it seems to be layering out a little bit. So you've seen this, or at least you've seen pictures like this. It's all we're talking about. Is those layers in the rock. Now, we talked a little bit about radiometric decay, right? Decay series is how you can tell how old a rock is, how old a fossil is. They use similar but different things to tell how old a mummy is or something like that. Okay, we couldn't always do that. That's really only about 100-ish years old. But we've been trying to do geology for a lot longer than that. So way back when, I don't want to say made up a handful of rules. They observed a handful of phenomena and turned them into rules. Okay? Organizational kind of rules. We're going to talk about a handful of those. And if you took earth science in high school, you've probably heard these. The first one is called superposition. Superposition tells us, and this definition is kind of crummy, but it is what it is. We'll explain it. In an unaltered section of rocks, actually, that's a pretty good definition. In an unaltered section of rocks, the oldest rocks are on the bottom and the youngest rocks are on the top. Anyone like to explain why that is? Pretty straightforward. You don't have to raise a hand, just shout it out.
People that rock was formed first, and some they were there first to go to the bottom.
Yeah, what he said. Simply put, the stuff on the bottom was there first because it's on the bottom of the pile? And you're like, well, duh. Yeah, there's a lot of those well, duh moments in this section here. But somebody had to say that it applies. Okay? So, you know, it makes sense after the fact. Well, yeah, of course. Okay, but it actually applies here. Oh, all right, sure. And it's helpful. So going back to this, what we're more or less saying is that the rocks up top are the youngest, the rocks on the bottom are the oldest. Why is that true? Well, because the ones on the bottom were there first. Unless somebody came over, lifted up the thing, set something underneath it. You know, that happens. You could have some serious, mangling of rocks. We've seen it. Maybe you've driven by really contorted sections. Stuff happens. Land shifting will sometimes lift something up on top of something else, and you got to check. You got to look around. But this looks fairly uniform. Not one of these things stands on its own. You always got to check. I used to give the example, but he hit it right on the head right off the bat. Think about your mail piling up, okay? Every day the mail comes in, you might look through it real quick for a bill, see if there's anything important. No, okay, throw it on the table. Next day, same thing. Next day, same thing. Next day, same thing. Friday, Saturday comes along, you're like, oh, let's get some pizza. Hey, I think some coupons came earlier in the week. All right, we'll go get them. What are you going to do? You're going to start at the very top of the pile? No, you're going to look maybe in the middle or down even lower. Why? Because they came longer ago. Now, if your dog comes up, puts his paws up on the table, knocks everything over, you've got to pick everything back. Lord only knows where it is, right? But if it's unaltered, that's the unaltered part. Okay? So, that one's pretty straightforward. This one's mine. So what we're saying here is that the rocks up top, again, just like the other picture I showed you, are younger than the rocks on the bottom. Now, it gets confusing. You get all this rubble down here. Of course, that's a mixture of everything. That someday will turn into rock itself. And being out of all of those different rocks, that is the problem with dating sedimentary rocks. Okay, they're made up of pieces, parts that have been lying around for Lord knows how long. So we like to date igneous rocks when we can. Next, principle of original horizontality. Spellcheck hates that word, but it is, geologically speaking, correct. In an aquatic environment, sediments are deposited in horizontal layers. Now, I actually just went off about this a little while ago and made it sound like it's everywhere. It kind of is. All right, there's some exceptions out there in the world, but most sedimentary rocks are formed in an aquatic environment. And like I said, I argue that even in most non-aquatic environments we see horizontal layering as well, but so when we see something like this, and while I may have been standing sideways at that moment because it was a really slopey rock surface, I guarantee you that that one section, that outcrop there, that's what we call a hunk of rock sticking out of the ground, was definitely slanted, okay? So those layers were no longer horizontal. Something happened that either lifted up one end or sank down the other end or both. This is Utah, by the way. See what I mean about it looking a lot like Mars, short of the vegetation, of course, but... And then even in the foreground here in the front, you can see some layers. It's worn smooth by time and tourists, but you can even see the layering in there. And it's tilted all crazy. Living in the guardrail state, such as we do, we were pretty, not appalled, but surprised at the lack of, well, let me rephrase that, the places you could walk to in national parks that really probably should have had railings, but not in New York State. They would have put something up. Very least a strongly worded sign. Lateral continuity. This one is also quite simple, but it always confuses people, probably because I'm not explaining it very well, and I apologize. And also it has two levels to it. One is application, one is just straightforward. So we're going to talk about the straightforward first. I maybe shouldn't have tried to blend them into the same slide, is the issue. So don't worry about the stuff in parentheses right now. At least that first one. So a rock layer extends outwards or horizontally in all directions until it ends. Okay. So it's going to end at some point, but what does that actually mean? And I'm going to come back to this in a second, so forgive me for switching slides real quick here. Okay. So we got some rock here in me standing underneath that big rock there. That's Great Arch. I forget what it's called. We're in Arches National Park here. So we got this rock here. And we got that rock behind me that we were actually just looking at a couple minutes ago. Then we got all that rock in the background. All right, what lateral continuity tells us is that, let me use the mouse so the folks at home, is that, here, mousey, there you are. This rock is the same as this rock, is the same as that rock, and probably the rock back there behind that. It's all the same layering. I mean, as long as it looks the same, as long as it's the same kind of rock, so on and so forth. Again, we have every reason to assume, until proven otherwise, that it's all the same rock. That helps you a lot if you're out there mapping this or trying to learn about this area for the first time. All right, you don't have to hike necessarily all over Tarnation. You could do a little alpine geology, as we call it, and find a nice high place and look around. Sure, you ought to go check spot sample here and there. Okay, but it should be the same rock. And again, that helps you to make, and even that rock in the far, far, far back right there. Now, it might be difficult to believe that that can get worn down that much. And why do some areas stay and some don't? Happens. Why, when you build a sandcastle on the beach and the wave comes through, does some of it stay and some of it doesn't? Got packed a little harder, the water hit it slightly differently. There's a handful of reasons. Because if it is, again, arguably the point we're trying to make, the same rock, why wasn't it all erased? It is just random. All right, now let's take that to an application level. Let's go back a slide again. So a rock layer or environment extends in all directions until it ends. Now, wait a minute. That makes sense. You've all been, everyone here not been in the woods, forest, whatever? Does that forest go forever? Yes? Wow, that's a scary forest. But at some point it's going to end. It's going to be, a field or a stream or a parking lot, whatever. But it ends. The same thing with the field. The field will blend into something. A marsh will turn into a lake or a field, depending on what direction you go. The desert, even though it could seem huge, will eventually stop being a desert and turn into another environment. What we're trying to do here is make the connection that rocks are products of an environment. All right? Not all environments produce rocks. Sometimes they actually erase rocks. Okay? We call them depositional environments. I don't want to get ahead of myself, though. And then there's erosional environments. But environments can produce rocks. So rock layers are the environment. They're what's left of the environment. So if we see nothing but sand for miles and miles around, what kind of environment maybe could we think that used to be? There's a couple options, as far as you guys know. Huh? So a beach, an oceany area, sure. And what else? What else has a whole lot of sand? A desert, okay. Are there other options? Sure, but those are the first two. Remember, always go with the easiest thing first. Check it out. So this was some sort of environment that produced sand, that had a lot of sand in it, so on and so forth. And that sand got compacted down to make sandstone. So all we're saying is that before this was rock, this was a desert. It's still a desert. Or it was a beach environment, okay, some sort of thing. And at some point, that beach ended and it turned into something else. So this rock layer should end. And when this rock layer ends, we'll find probably a different sort of rock. And that would be a different environment. And here's where it gets really freaky. All right, just like nowadays, as we were talking about walking through a field that starts to get marshy, and then if you keep going through that marsh, you might find a lake. Just like today, we have these progressions, these blends. Well, the world was like that then too. And the rocks, so by looking at these rocks, we could reconstruct the environments. So there's actually two on this slide. I need to rewrite this a little. This is a fairly new PowerPoint. Principle of cross-cutting relationships is a lot bolder because this is, I guess I decided at that moment, the main word, okay? And what cross-cutting relationships tells us is that the disrupted pattern is older than the disruption. Sounds very philosophical. What does it actually mean? It means you can't cut through a field that isn't there. Right? You cannot put a big old stripe down the center of your lawn if the lawn isn't there. How else can I say this? Let's say you're looking at a giant cliff of sandstone and there's a big old igneous intrusion in the middle of it. Which one came first? The sandstone cliff or well, not the cliff, but the sandstone, or the intrusion? The sandstone. Why? Well, because it needed something to intrude into. Otherwise, it just would have flowed all over and it would have looked like something else if there wasn't any rock there. Again, duh, okay? But somebody's sitting there staring at this cliff face. They've got the job of trying to organize it. How old is this? How old is that? They're going to start with superposition. Okay, the crap on the bottom is older than the crap on the top. We got this big old igneous intrusion in the center of it that should be younger because the rock had to be there for it to intrude into. Now, if it doesn't go all the way through, it can get confusing. Because you're like, okay, well, the rock at the top, maybe it was there, maybe it wasn't. Maybe it just ran out of oomph and it didn't go any further. So, again, it can get very complicated. But at this level, we're trying to keep it simple. So as an offshoot of that, sort of a parallel rule, if you would, we have the principle of inclusions. The inclusion is older than what's included, than what it's included in. The inclusion is older than what it is included in. What's older, the chicken McNugget or the chicken? The chicken. What's older, the hunk of sandstone or any one of the thousands of pieces parts inside of it?
The pieces parts?
The pieces parts. Otherwise, you ain't making sandstone out of it. All right. So none of these are really hard or tricky. Maybe, like I said, short of lateral continuity. That's actually about the process. But they're all very straightforward assumptions. I hate even to call them assumptions. I don't want to call them truths, though, either. No, they're principles. They're tenets. They're ideas. All right? And it's putting all of these together that it has helped those people hundreds of years ago, a couple hundred years ago, organize all the rocks around them, mainly in Europe. But we got over to America and started doing that stuff too. And the crazy part is, even though they were out there with mules and compasses and sextants and whatnot, that now that we can go out with our isotopic dating and our GPSs and our hover cars and everything else that we have cool now. We never did get hover cars. They promised us hover cars, though. Now that we can go out there with all that stuff, we're finding out they were right on. Okay? They were right on. Yeah, they couldn't have said this was 5 million years old. But they said this was older than that, is older than this, and so on and so forth. So these rules work. and they continue to work. We still use them. But now we can verify, too. Now, all of these work. Now, did you guys get these in Earth Science or no? Some of them? All of them, they sound familiar-ish? Depending if you were in honors or in regular or no? All right, well, I know you got this next one, but I just wondered if they got into the weeds with it. I know it was like 4 years ago, too, for some of you, so. We can do all of that because, I know you don't say believe in science, but because we believe in this. Uniformitarianism. Uniformitarianism always gets boiled down to the present is the key to the past. That really, you guys are capable of more than that. They say that because what they mean is that the second bullet, the processes, the rates, the world as we see it, observe it, okay, happening around us now, it happened the same way in the past. So gravity still worked in the same manner. So sediment piled up in the same manner. Water flowed in the same way. So we could assume that water transported material and or broke down material in the same way, and so on and so forth, right? So by observing the world around us, we can make some observations about the world of the past that we weren't there for. All we see are the rocks that are left behind. Now, I don't get into it in this slide because I do have, in this presentation, because we do have a geologic time PowerPoint, which I'd forgotten about until about 10 minutes ago while I was talking to you. We could arguably put that in before the next test. I'm just worried it's going to be way too many questions. Anywho, so in the off chance that I don't actually even do that chapter, I do want to just go off on a side note for a minute. So we didn't really stick with uniformitarianism. It's there. It's a central theme. Kind of like evolution, right? I'm in a position where a lot of people want to argue with me about evolution, or at least tell me they don't believe in evolution, and so on and so forth. And that's fine. You do whatever you want to do in life. Okay? But when they start talking and arguing with me about what Darwin said, I'm like, okay, that was a long time ago. How about some of the newer work we've done? Well, no, Darwin, no. All right, so uniformitarianism is the same way. It's a wonderful foundation. Could you unequivocally say that the processes and rates that occur now have always occurred? No, why? What happened? What could have happened, or so on and so forth? Bless you. I hear some mumbling or muttering. Say it out. You might. I don't make a whole lot of fun of wrong answers. Well, yeah, but I mean, like, what kinds of? Has rates of volcanism always been the same?
Not necessarily.
Yeah, not necessarily. Very true. There were some periods when it was much more active than others. Again, around the time of the dinos going out, we see a whole lot of volcanic activity going on. Around about 65 million years ago or so.
Part of me wants to say that doesn't really fit in this, though, because volcanism doesn't really change the laws of gravity, does it?
No, but it changes what you see on the rock record, though. It changes, if you only had access to rocks 65 million years old, let's put ourselves back a couple hundred years when it wasn't so easy to travel. All right? You could make an assumption that volcanism was incredibly prevalent, just as an example. All right? And arguably it had a huge effect, not just on the local area, but with the clouds of ash going up, and it can go into blotting out the sun, causing the food chain to collapse and so on and so forth. So there's lots of larger effects from that. Similarly, we talked, I think, a little bit when we did the Everything You Wanted to Know About the Earth and Then Some lecture. We talked about the period of heavy bombardment. I may not have called it that. But you look at the moon, you see all the craters on the moon, right? We have to assume that we got hit just as much, okay, just as frequently. If not, yeah, more, because we're bigger and so on. It's more we're bigger, we have more gravitational pull, we're easier to hit. There's a handful of reasons. Again, luckily, that was an eliminating sort of process. Once a asteroid or meteorite, we got into a discussion about asteroids versus meteorites. Once that hits, it's sort of out of the equation and so on and so forth. All right. We don't get, thank God, we wouldn't be this far in life if it did happen. We don't get hit that frequently anymore. So that rate has changed. So what we've moved on to is something called actualism. Okay. Again, it's sort of what actually happens. Because there's catastrophists out there. There's the other. So uniformitarianism says slow and steady wins the race. Catastrophists say big, huge, scary changes, big, huge, scary events make the most change. And again, there's something to that. But that, thank goodness, isn't so frequent. So you get a mixture of slow and steady, and oh my gosh, this meteorite just crashed into us. That's going to change things. So we end up with, they came up with the word, not me, actualism. What actually happened, I guess, is what they're going for. So it's not like somebody goes out and argues uniformitarianism. That's silly. But it has evolved. It has changed over the years. Just remember, they laughed Wegener off the stage when he was presenting plate tectonics. They're like, how the hell are the continents moving? That's absurd. What, are they floating through the oceans? That's how we got continental drift, right? Remember, they used to call it that. So he didn't have a mechanism. They thought he was ridiculous. He was right. So things change. All right, so that's it for principles. Like I said, if and when we do get a chance to do geologic time, you'll see some of these again. We kind of cruise through that section of it, focus more on the radiometric stuff because it's newer. But we need it to help us understand these rock layering ideas, concepts, basic concepts in stratigraphy. So before we leave that, change gears, any questions about any of these principles? All right, you will see them. Probably as I give you the definition and you need to pick out the vocabulary word that it is, okay? All right. Rocks. So you may have heard the word rock formation. You didn't think it actually meant something, but it does. It's a grouping, all right? You might say, oh, look at that cool rock formation. You might say, look at that cool pile of rocks. Both are equally as likely, I suspect. But a formation in context does mean something very specific. So it's recognized, I don't have that word in there, but it is a recognized group of bedding planes, all right, of either one rock type or a pattern, a repeated pattern of rocks. Formations are named, location and rock type typically. Every so often somebody will get really greedy and throw their last name in or something like that, but they do that. They tend to do that more with fossils and stuff. So, great example, Utica Shale. What kind of rock is Utica Shale, you suspect? Shale. Where do you think the best example of it is? Utica. Yeah, you'd be sort of right, but in Utica, the Utica Shale is like actually incredibly buried. But there's a few places it sticks out, and it is wonderful to see. But and it actually goes all the way into Ohio and then some. That's what they're back when fracking was like in the news and everything like that. It's thousands of feet down, but that's what they were hitting in Ohio for fracking was the Utica Shale. So that's if it's one type of rock, right? If it's a repeated pattern, then they just use the word formation. The Albany Formation. All right, well, we know it's located in Albany, but we got to Google that sucker and see, oh, it's limestone shale. Oh, okay, that's cool. You got to look that one up. So if you see the word formation, it's multiple types of rock. But if it's only one, they're going to just tell you what it is. And again, we have to be happy that for once they're keeping things simple. These little badges are too small to see. Kaibab limestone, Coconino sandstone, Toroweap formation. This is Grand Canyon stuff. I was actually just seeing this last July.
What is contacts?
Give me a sec. What do you think it is? Looking at where the black lines are. Contacts are the black lines.
Oh, just areas between the different formations.
The boundaries.
Yeah.
What do they represent?
Different time periods? Just
True.
like
True.
that falls off the top.
Yeah, that would be true because that was arguably a surface for some point. Anybody else want to throw something out there? Yeah, but what does that represent? All right, let's look at, unfortunately, we're going from Kaibab limestone to a formation to, let's pretend the Coconino was right under the Kaibab limestone. So we went from Kaibab limestone to Coconino sandstone. We're going to have to draw a black line in between there because what happened? Different rock type, which means what changed?
The environment.
Yeah. All right? Yeah. So rocks are the products of environments. So, where do we tell you limestone comes from?
Seas.
Oceans, exactly. Seas, oceans, whatever you want to call it. All right? So to change from an ocean to sand, yeah, you could go as drastic as a desert, but what else makes sand we were just talking about? Oh, what's that dry part, though, called?
Beach.
The beach, all right? So, to go from limestone to sandstone, we're going from ocean to sand. If you were to drill a hole down through that and make one straight place, in other words, you're in one position, all right? If you stood there for all of the time that was going on, you would go from standing on the beach to being 50 feet underwater. What does that mean just happened? To whether, let's see, so what happened last? Because limestone's on top, so the ocean was over you last. So if you were standing there and it was sand, and 10,000 years later, let's make up a number, you're now 50 feet underwater and you haven't moved, this is huge application stuff. You guys have been doing good though so far. Sea level rose, right? But wait, that senator said that's not a thing. Huh. Weird. All right. And so what do you think is in that formation then? If you got limestone on top and sandstone on the bottom, you're probably seeing a little bit of back and forth.
Some combination
Yeah.
of the two.
Exactly. All right, it blends until it completely changes. Might be a little shale thrown in for good measure. Remember, shale's mud. There's going to be mud there. Yeah. So that's why we try really not to bother arguing with people like that, because we know it's true. Or there's something else really bizarre happening. Somebody could have, just laid down a huge hunk of limestone there for no good reason, I suppose. But those black lines could also indicate gaps in time. I'm not sure if we get to it in this or not. I don't think we do. Because that could have been, remember, that was a surface. Any layer here was the surface for some point in time. And you don't know how long, going from the Coconino to the Toroweap there, all right, you could have lost 10,000 years. Just like, on the cover of your lab book. All right, you've got the shale down at Little Falls. That hasn't been shale in, I forget the date, 360 million years, 460 million years. I forget how old that is. It's old, okay? And what's there now? There's grass, there's fences, there's houses, there's all that stuff. If, worst case scenario, I don't think we'll get the water in this high, but let's just play along. All right, all the caps melt and the oceans come back in. You're going to start depositing sediment on there again. You're going to have one of those little black lines. There'll be a gap of 400 million years. So you really got to look, you know, when you're out there doing this stuff. And that's where, again, it's really nice to have that radiometric dating. Even if it is sedimentary rock and sedimentary rock is really crummy to date, you're going to notice a big jump like that. So, all right. So we don't get to apply a whole lot of stuff in this class. So when we actually have a chance for you guys to think a little bit, yeah, actually here. It is in here. The folks watching the recording could actually see the next slide, so they knew this was there all along. You know, I didn't even see it. So that last bit that I was talking about, the gap in time, there's another vocabulary word for that one. It's called an unconformity. This font doesn't lend itself very well to bold versus not bold. But that bottom there is supposed to be bolder. And there's a little bit more about unconformities on the next slide. We good? Ish. So an unconformity, again, is a gap in the rock record. Therefore, it's a gap in time. It could be a weathering event, in other words, erasing. Or it could also just be nothing's really getting deposited. Right now, you just look out this window, we're in the no deposition sort of thing. Yeah, there's some sediment building up here or there, but not much. And arguably, we're wearing more stuff away than we're depositing. So imagine you had some sort of job where you had to compile a monthly report or an annual report even, and for whatever reason, you know, you're missing the third week in January. If it's a monthly report, you're going to have a gap in that report. Or, you know, if it's a year-long kind of thing, you'll have a gap of that. So that's what these unconformities are. We're not really sure what happened in your office. We don't know why that report's missing. Could be something good. Could be something bad. Could be just an accident. We don't know. You need to look into it. All right. Before I started, we're changing gears again. I just want to make sure that I'm going to hit pause for a second here on the recorder.